Let us continue our discussion with the Peterson coil. Already we have discussed about the RC ground. RC ground means the arc is maintained because of this capacitive current flowing in this path because of the ungrounded neutral. So Peterson coil, it provides the protection against this RC grounds. Let us see how it is. So also known as ground fault neutralizer or arc suppression coil. So you can observe like this. You can see an inductor which has a tap changing also option that is connected between neutral to ground. Okay, it is an iron core reactor connected between neutral point and the ground, and capable of being tuned with the capacitance of the healthy phases. So this inductance value is tuned to the capacitance of the healthy phases to produce resonance when a line to ground fault occurs. As I said, whenever the fault occurs, healthy phases voltage becomes √3 times of the actual voltage. So normal faulty phase voltage anyway becomes 0. Now it will be subjected to high voltages, voltage stresses will be there. If you leave like that for a long time, so the insulation of that will be damaged, as well as it leads to further subsequent faults. So it is mainly used to prevent arcing grounds, which led to the over voltage on the systems with an ungrounded neutral especially. So Peterson coil makes arcing ground faults self-extinguishing. And in case of sustained ground faults on of the lines, it reduces the fault current to very low value. That means if there are arcing grounds, that will be self-extinguished. If there are any other faults, their fault current is reduced because there is a connection between the neutral to ground, so that healthy phases can be kept in the operation even with one line grounded. One line grounded healthy phases can be maintained for some more time without any problem. In order to select the proper value of the inductive reactance, depending upon the length of the transmission line, and hence the capacitance to be neutralized. So we have to select this value depends upon this length of the transmission line as well as the capacitance to be neutralized. So Peterson coil provided with tappings. You can have different tappings which are not shown here. So we'll discuss about this phasor diagram. So if you see here, in an ungrounded system, when a ground fault occurs in any one of the lines, the voltage on LD phases becomes √3 times of the phase voltage, as we discussed. Hence, the charging current becomes √3 times of this current in that line per phase, where I is the charging current from line to ground. That means IC. This is the charging current. If you observe here, VR, VY, they are LD phases. VB is a faulty phase. Therefore, VR, VB, if you write VB is at ground potential. That means 0 voltage. We have not drawn like this. It is at ground potential. So, if you have a neutral to ground connection, the neutral is at ground potential like this. So, this is the phasor diagram you can understand. So, you can see the currents with respect to VR, VY, they will be drawn like this, √3 IA. And this is the √3 I. This is √3 I with respect to VR, VI. So the resultant current is 3I. If you calculate the vector addition. So this 3I is the current flowing in the capacitor. So that should be neutralized. So to neutralize this charging current, we should have an inductance whose current is equal and opposite to this current. Then this current will be reduced. So the phasor sum of the charging currents is 3 times of the normal line current. That's what I said. Therefore, what is the charging current? 3I, which is equal to 3 into phase voltage divided by XC. XC means 1 by omega C. That is 3 Vp omega C, where IC is the resultant charging current and I is the charging current of the line to ground. Suppose if L is the inductance of the Peterson coil connected between the neutral to ground, then what is L? IL Vp into, that is XL, that means omega L, Vp into omega L. So therefore, if you equate these two currents, then what happens? If you equate these two currents, then it becomes, here by Vp by omega L, it is not Vp into omega, some by is missing here, Vp by omega L. Therefore, in order to obtain the satisfactory cancellation of the arcing grounds, the fault current IL flowing through the Peterson coil should be equal to resultant charging current. IL should be equal to IC. Therefore, Vp by omega L is equal to 3 Vp by omega C. L is equal to 1 by 3 omega square C, where L is the inductance of the Peterson coil. It is very important, a simple derivation, and you will get problems on this Peterson coil also. So this is the inductance to be connected to counteract the RC grounds. So if you say 33 kV 3 phase 50 Hz overhead line 60 km long has a capacitance to ground of each line 0.015 microfarad per kilometer. So determine the inductance in kV rating of the Peterson. You know what is the inductance formula? First, L is equal to 1 by 3 omega square C. What is C? 0.015 microfarad per kilometer into 60. You do it, you will get L. From that, XL can be obtained. So from that, for ground fault, the current in the neutral is given by Vp by omega L. You will get neutral current. So the voltage across the neutral is given by this voltage per phase into neutral. 33 by root 3 into neutral current. So this is the kVA rating of the Peterson coil. Okay. So like this, another problem is given. 50 Hz overhead line with capacitance 1.2 microfarad. Use ground fault neutralizer. That means Peterson coil. Determine the reactance to neutralize the capacitance of 100% length of the line, 95% length of the line, 80% length of the line. So for all these things, simple is, you know, omega L is equal to 1 by 3 omega C. If you are taking 100% length of the line, you take capacitance direct 1 point into 10 power minus 6. You calculate the inductance. If you want 95%, then simply you multiply 1.2 with 0.95. You will get this inductance. If you want 80% length of the line, just multiply this 1.2 with 0.8. Therefore, you will get this inductance value. So this is the simple way they have asked the reactance. So directly we will get the reactance value. These are very simple problems you can get in the Peterson coil. In the competitive exams also, you can find the problems of Peterson coil. So let us go to the surge diverters. So surge diverters means which diverts the surge to the ground. So they have simply, it is a representation of a circuit, a spark gap, and nonlinear resistors. Whenever the surge falls on here, so if the voltage is more than the breakdown voltage of the gap, then what happens? This gap conducts and the surge flows. This is a nonlinear resistor. This combination is called nonlinear resistor. Nonlinear resistor means for high voltage. For high voltage, it acts as a conducting path. That means it offers low resistance. For low voltage, that means power frequency voltage, it does not allow to the ground. That means it acts as a high resistance. That means low voltage, for low voltage, the normal voltages, high resistance. For high voltages, it acts as a low resistance path. That is called non-linear resistor. That you can understand in the resistors discussion. So what are the basic properties? It should not pass any current at normal, abnormal, or abnormal power frequency voltage. That is normally 5% more than the normal voltage. It should not pass any current to this. It should break down as quickly as possible after the abnormal high frequency voltage arrives. It should not only protect the equipment for which it is used, but it should discharge the surge current without damaging itself. It should protect itself. It should protect the equipment also. It should interrupt the power frequency flow of current. That means if normal power frequency current flows, it should not go like this. It should go to equipment directly. It should interrupt the power frequency flow of current of the surge discharge. Once the surge is discharged, if normal current goes, that should not be earthed. So it should interrupt the power frequency flow of current, as I discussed. There are mainly three types of diverters: rod gap, protector tube, or expulsion type resistor, and valve type of lightning resistors. So already we have discussed about the rod gap. Now we are going to discuss about the expulsion type of lightning resistor and other resistors now. So what is the expulsion type of lightning resistor? We can observe here the picture. So I have given the total operation with the simple points here. So it is an improvement of the rod gap. We have seen some problems in the rod gap. Even if the arc is extinguished, there is a flow of arc current from the line to ground, so that LG fault, line to ground connection will be there. There is a possibility of the LG fault. So such type of problems can be avoided by this design. So what is this containing, it is having series gap, one series gap, which is external to the tube, which is good enough to withstand normal system voltage. That means for normal system voltage, it should not break down. Thereby, there is no possibility of corona or leakage current across the tube. A normal frequency voltage, if it appears across on the line, there is no diversion. And a tube, you can see a tube which has fiber lining. Tube has fiber lining on the inner side of the tube, which is highly gas evolving material. Whenever the arc occurs, it produces more gas. And you can see a spark gap. There is a spark gap in the tube. So 1, 2, 3. And you can see enter point here, vent opening at the lower end for the gases to be expelled out. Okay. So let us see the operation. So it is desired that the breakdown voltage of the tube must be lower than that of the insulation for which it is used. That means before the insulation breaks down, flashover, it should break down. That means it should conduct. Definitely its breakdown voltage is less than the insulation strength. So when the surge voltage is incident on the expulsion tube, on the series gap, then the series gap is spanned. It allows arc is formed between the electrodes within the tube. Then what happens? Heat of the arc produces, that means it produces heat of the arc, vaporizes some of the organic material in the tube wall, causing high gas pressure to build up in the tube. Then heat produces gases. That gases, how they are produced? Because of heating of the organic material of the tube. The heat of the arc vaporizes some of the organic matter of the tube wall, causing high pressure gas to build up in the tube. So the resulting neutral gas creates a lot of turbulence within the tube and is expelled out from the open bottom vent of the tube, and it extinguishes the arc at the instant of current zero. So arc will be extinguished. So at the instant of current zero, what happens? There will be restriking voltage. Okay. So the rate of buildup of insulation strength is greater than RRV. Very high currents have been interrupted using these tubes. The breakdown voltage of the expulsion tube is lower than plain rod gaps of the same spacing. So that means if you take a rod gap of same spacing, if you take the expulsion tube, it will break down quickly compared to rod gap. It is a better protecting mechanism for the same spacing. With each operation, what happens? The inner lining subjected to arc, and that will slowly deteriorate. The diameter of this tube will be increasing because this is subjected to arc heating. The diameter will be increasing, thereby insulation characteristics of the tube will decrease. Characteristics will be decreased. So if you take the volt time characteristics, they are better than the rod gaps. So these expulsion